Hello, fellow learners. We are going to do chapter 23 in this video. Chapter 23 is going to talk about means. And you might remember in chapter 18, we talked about the sampling distributions of proportions and of means. And then we spent chapters 29 through chapters 19 through 22 talking about proportions and now making confidence intervals and doing hypothesis tests. Now we're going to just go back and we're going to start doing the same thing on means. And I think I mentioned this in the last lesson. All of this should be pretty straightforward if you understand what a hypothesis test is and what a confidence interval is. There are some slight differences and we're going to talk about them today in chapter 23. So I think it is time to get started. So here we go. Chapter 23. Okay, so chapter 23, we're going to do one sample t-test. So remember, when we were doing proportions for the last few chapters, we started with one sample test and then went to two sample tests. We're going to do the exact same thing here. So chapter 23 is about one sample, what we're going to call t-tests, and I need to explain what that's all about. So here we go. So here's an example. Let's see if you can take a second and read it. So you are making, this is a cookie company and they have a machine that puts in the sugar and they want to make sure that the sugar has 10 grams of sugar for every cookie. So they take a sample of 25 cookies to measure the level of the sugar. So first of all, you need to get the data. So you'll find it in data sets in Canvas under sugar. So you're going to need to pause and go get it. So the file in there is an Excel file. But you need to not have it in Excel. You need to have it in some statistics package like Minitab or something else. I'm putting it there not as a Minitab file because I know some of you aren't using Minitab. So it's there as an Excel file. Now, if you are using Minitab, you have two choices. You can download it as an Excel and then open it in Minitab, or you can download it as an Excel, just copy the data set and then copy it into Minitab. So I'm going to give you a second to do that. I'm going to do it too. So go get that data set. Okay, so I'm assuming now that you have found the data set called sugar. And so it is just a list of cookies with how many grams of sugar there are in it. Okay, so the first thing you have to notice is that yes, we have switched to means. We're not asking a yes or no question about each cookie, which we would be doing if we were doing proportions. Instead, we're measuring a number in each cookie, in this case, the grams of sugar. So we have switched from proportions now to means. Okay, well, let's look at this for a second, okay? So let's see if we can remember what we need to know from chapter 18, because we're going to need to remember the basic properties of the sampling distributions of means. And I know we haven't done it for several chapters, so let me just review it. I hope if you've been watching these videos, you remember this table from chapter 18. And on the left were proportions, and here are the formulas that we've been using the last couple chapters. But now we're going to switch it to means, and so we need to remember now these three ideas, okay? That the mean of the sampling distribution, so let's pay attention to the notation, mu x bar, that means if I went out and took samples over and over again and measured the sample mean each time, the mean of all those sample means would equal the mean of the population. So that's an important idea, mu x bar equals mu, and it's true if we take the sample without any bias. Then we prove this formula here, that the standard deviation of all of those x bars equals the standard deviation of the population over the square root of the sample size. And that's true if the picks are independent. And that means if we're sampling, that means the 10% condition has to be met. But in general, it has to be independent. And then we learned the central limit theorem, which told us that this sampling distribution of means will be approximately normal if n is big enough. And we're going to use these three ideas now as we go ahead and talk about chapter 23. So here we go. Okay, first let's just look at the data. So why don't you do this yourself? Why don't you go to your Minitab file, which is right over here. And, let's just we should start by just investigating the data set. So that would mean getting basic statistics. So I'm going to basic statistics, and I'm going to ask it for sugar. And look, there's my mean and my standard deviation. Here's my basic numbers. Okay. And I guess we should make some graphs too. So I'm going to go to graph and histogram, choose histogram, tell it to use sugar. There's a histogram. I don't know, maybe a box plot. You can do whatever graphs that you want to look at, but it's always an important idea to just look at the data before you begin. So I notice, I noticed it was supposed to be 10, right? That's what the machine said, but the average of this sample was 11.884, so that's not 10. But remember, this is just a sample, right? This is the whole logic of what we've been doing, okay? We call this statistical inference, okay? What can the fact that we got 11.884 tell us about what we think about what the machine is doing, right or wrong, okay? Standard deviation, so it has actually a great deal of variation, right? The mean is 11.8 and the standard deviation is almost 4. So there's a lot of variation in there. And then I look kind of at the shape. That looks fairly well behaved, I would say. We'll get back to all that in a second. Okay, so that's always should be your first step, is just take a second and look at the data set that you're dealing with. Okay. All right, I'm going to switch back here. And let's take a look at this. Okay, so I've copied that information back over here. Mean, standard deviation. All right, so let's get started and do this now. So I want to do a hypothesis test because I do see the mean is different than 10, but my basic question is that difference so big that it's unlikely to just see that difference by chance? Okay. I don't know, because there is a lot of variation in this data set. The standard deviation is almost 4. So we're going to learn how to do this. Okay. Well, there are your hypotheses. That's step 1. Okay. The mean is 10. And why am I doing not equal to 10? Right? Because I wasn't trying to test if the machine was putting too much sugar in or was putting too little sugar in. I just want to know, is it accurate? So my question, this should be a two-tailed test about whether mu is 10 or is not 10. So there are the hypotheses. All right, you remember there are 5 steps to doing this, right? Hypotheses, assumptions, work, conclusion, decision, and then conclusion. Okay, so I've just done 1. Hypotheses. Okay, only 4 more. Okay, second is assumptions. Normally we would do these here. I'm going to return to these after I explain to you the basic mechanics about doing a means test, but we would do assumptions here normally. We'll return to that. Okay, so now let's talk about the work. Okay, so we have to get, if we're going to do it the same way we've been doing all these problems, we have to get a z-score. And we know that's what the z-score is, right? The estimate, what we got, minus the null hypothesis divided by some standard deviation. Same as it always has been, okay? So, what was the null hypothesis? Well, the null hypothesis was 10, was it not? Okay, we were trying to test whether the machine is right. That was 10 grams per cookie. And what was our estimate? Our estimate was 11.884. So 11.884 minus 10 is the numerator. That's the same as it's always been. Okay, and now here's the question. Do we know the formula for the standard deviation of the sampling distribution of X bars? Oh, here's a picture of it. And there's the formula, isn't it? So we just saw in that table before that the standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of n. So there's the formula. And I want to do a two-tailed test. So here's 11.884. I need to figure out this area. It's a two-tailed test, so I got to find the symmetric point over here, but these two areas are going to be the same. So this is all I have to do. It seems like I'm just ready to roll, right? I don't have any issues, okay? But wait, there is an issue, isn't there? Is that you don't know sigma. You don't know sigma. You don't know the standard deviation of the population. And to figure out this formula, I would need to know what it is. If I did know sigma, I would argue with you we are done right now. Okay, I would plug in sigma right there. I know n is 25. I'd get a z-score. I'd look it up on the chart, and we would be finished. Or I have to write a conclusion, and we would be finished. Okay, the problem here is that we don't know sigma, right? We did not have this problem in the proportions test because this formula involved p, which was the parameter to begin with, right? So we were supposing p was a number. But here we have two independent ideas, the mean and the standard deviation. Even though we're supposing the mean is 10, sigma could be anything. Sigma is independent of what the mean is. So this is kind of a bigger problem than we had in proportions. What do we do here? Okay, but I don't know. What would you do? I wish we were in class so I could ask you. What would you do? Do you have some number that's an estimate of what the standard deviation of the population is? And I'm going to say, yes, you do, don't you? Isn't it in this list right here? Where is it? It's right there, right? S, the standard deviation of the sample, in this case 3.959, is an estimation of what sigma is. So why not just take 3.959 and substitute it in for sigma? That seems like a reasonable plan. If we took a random sample, it would seem like the standard deviation should be somewhere around the standard deviation of the population. And so maybe we should just make this fudge. It would be a standard error, will it not? Because we don't have the standard deviation anymore. Now we have some estimate of the standard deviation. But that seems like the right way to go about doing it, okay? Is to just, instead of sigma, use S and understand that we're now estimating the standard deviation of the sampling distribution, okay? And actually that is where we're gonna head. But first I got to tell you a story about all this, a historical statistical story, okay? Oh yeah, so yeah, I mentioned that. This is S, not sigma, okay? So you need to meet this gentleman here. He's one of the giants of statistics history. His name is William Seeley Gossett, attractive looking man, I would say. Let me tell you a little bit about William Seeley Gossett. So Gossett was a student at Oxford in the early 1900s. And he was studying math, and he got very interested in statistics, which was a very new field, okay? And he starts to work, and he starts to work with some of the ideas that were being developed about distributions and hypotheses and all this stuff that we're studying in this course. Okay, and he graduates from Oxford, and he decides that he wants to go get a job because unlike some of the other gentlemen who were developing statistics, he was not a rich guy, okay? And so he needed to go get a job. And what he decides he wants to do is go work in industry, okay? To use statistics to like better the industrial process, okay? Industrial statistics today in 2020 is a very, widely used skill, okay? Widely used field. Most big companies have a department of maybe quality control or industrial statistics, but at the time, almost no companies did, okay? And so Gossett wanted to go work for some company to do what we would now call industrial statistics. So he goes out and he gets a job, and where he gets a job is at a brewery, Guinness Beer. And Guinness Beer hires him to like be a math guy, okay? And in fact, they hired they were a very forward-thinking company, and they hired a bunch of scientists, okay, to work on their processes to make more profitable beer, better tasting beer, to improve the delivery systems, all that kind of stuff. And they were really the only, at least the only brewery that was doing this, and they were probably maybe one of the only companies who was actually using science in this way. And so they wanted to get in on this new field of statistics. And so they hire William Seeley Gossett. And so he graduates from Oxford, and then he goes and he starts working at Guinness Beer. And he starts doing a whole bunch of statistical work on their production, on the seeds they're using, and on their delivery, all this kind of stuff. William Seeley Gossett is doing experiments on. And it's going pretty well, but he notices that he has a problem. He starts to think that he has a problem. And the statistics that had been done up until now was all on very large data sets, okay? Data sets like, you know, the head circumference of every man in the British Army, okay? Big data sets. And William Seeley Gossett, because he's now working in an industry, is forced to be doing work on much smaller sample size, okay? And he starts to do some of these processes like hypothesis testing, but he's using very small data sets. And he's concerned about this. And so he goes and he starts working with this guy right here, Karl Pearson. You remember the correlation coefficient? I hope you do, R. That's called Pearson's correlation coefficient, named after this guy. And Pearson is one of the big statisticians. He's working for a guy named Sir Ronald Fisher, which we'll meet in a second. They have a journal called Prometrica and an institute where they're, you know, basically inventing what we call statistics nowadays. And Gossett goes to Pearson and says, you know, he has this like issue that he's worried about doing the procedures that he knows on small data sets. And Pearson says, well, you know, don't do it on small data sets. And Gossett says, well, I have to, because I'm working in industry and we don't necessarily have the biggest data sets. And so Pearson says, well, Gossett, why don't you just like do some math experimentation? And this was a weird concept at the time, okay? But what Gossett does is he decides what he's going to do is simulate taking samples. And he does this with pieces of paper and a calculator. Okay, the calculator he used, by the way, is this real old-fashioned gear calculator. It's a mechanical calculator. I actually have one at Blair that I got from the early 1900s. It broke, it jammed, the gears jammed, and so it's down in Mr. Street's lab because we were trying to unjam it. Okay, but he's using this calculator, and what he's doing is he's taking small samples of pieces of paper. He's just picking up pieces of paper, writing the numbers down, averaging them up, taking standard deviations, and then just writing it all down until he gets sample after sample after sample after sample. And he's starting to like create his own sampling distribution just through simulation. Now today with simulation on a computer, we could do this process in a second, but he was doing it by hand, okay? And it took him a very, very, very long time to do that, okay? And he does this under the supervision of Pearson, and he's doing it. He's still working at Guinness, but he's doing this like math work at night, and he starts to assemble these sampling distributions. Well, they're not really sampling distributions. I would describe them as simulated sampling distributions. And when he starts doing this, he really starts convincing himself that there's actually is a big problem. Okay, and that the problem is the sampling distributions he's getting, they look kind of normal, like we've been using in a Z distribution, but not quite. And he finds that their tails are a little bit fat. And what I mean by that is like if he's doing an experiment where he's expecting, let's say, a 5% type 1 error, he's finding that he's getting something a little higher than that, that the area under the curve in the tail is a little more than 5% when he's expecting 5%. And so he thinks that there's something going on, okay? And then he starts he starts making some hypotheses, okay? So he hypothesizes. To me, this whole story is just mind-boggling, the genius of William Seeley Gossett, right? The fact that none of this has been talked about, invented, And he's the one who's just hypothesizing about this. And he hasn't really done any like math. He's just done this with simulation. And here's what he hypothesizes, okay? He says the problem he thinks that he's getting more type 1 error than he thought is because he's substituting S for sigma. Okay, since he doesn't know what sigma is, and he does have a standard deviation of a sample, and he puts that in, as we were talking about a minute ago, he thinks that's where the source of the error is. And furthermore, he thinks that the problem is bigger when there's a smaller sample size, and that as the sample size gets bigger, we don't really have this problem. And the reason he thinks that nobody's thought about this before is that they were always using big sample sizes. And when you have small sample sizes, he thinks there's a problem. Okay, then he makes this huge hypothesis. And the hypothesis is that the normal model, when we do this substitution, the normal model isn't quite right anymore. And he hypothesizes that there's this other like mystery distribution out there, that it's kind of normal, but it's a little bit different. And he names it the T distribution, which, by the way, T stands for test, which is kind of peculiar because we now talk about the t-test, which actually means a test, which is a little weird. But he names this mystery distribution the T distribution. And he says it looks normal, but it's a little bit fatter in the tail. Furthermore, he says, the T distribution, unlike the normal, there's many T distributions. He hypothesizes this all from the like experimental data that he's just getting with his pieces of paper and his calculator. He suggests that there are lots of T distributions and that they're defined by the sample size. And so this is really important now. Okay, he's going to define them by what we call the degree of freedom. And so degree of freedom, we're going to talk about this a lot in the next few chapters. But degree of freedom is very simple. It's just n minus 1. Okay, so if you had one way to think about this is if you had a sample size of 1, there's no degree of freedom, right? Because sample size of 1 would just mean the population itself, right? And so the degree of freedom is simply n minus 1. Okay, so if I take a sample size of 20, I have a 19 degrees of freedom. And Gossett hypothesizes that there's a different T distribution for every sample size. Okay, and so there's, if you're taking a sample size of 20, he's going to say there's a T19, the T distribution with 19 degrees of freedom. And so these are his hypotheses. Okay, now he hasn't really done this with any math. Okay, and I want to show you now. Well, let me show you this guy. Okay, so Sir Ronald Fisher is works with Pearson, and he's who we think of now as the father of modern statistics. Okay, he's debonair, isn't he? Right. So William Seeley Gossett starts explaining this work to Fisher. Okay, and Fisher is quite intrigued by it. Okay, in fact, there's this famous letter that Gossett writes to Fisher in which he sends them his numbers, like the probabilities that he's getting from these simulated sampling distributions, kind of a simulated chart. And he sends it to Fisher with sort of a sad note that says, here are my numbers. I think you may be the only person who might care. Okay, and he sends them in, and Sir Fisher, like, he starts to realize, Ronald Fisher does, that like Gossett's really onto something, and that he has like developed a whole new distribution and a way to do some of these procedures using smaller sample sizes. And so Fisher thinks this is really, really important. Okay, and so he tells Gossett, like, you know, you've done great work here, William Seeley Gossett, and I'm going to publish it, because he has this journal called Prometrica, and he's going to publish it. And Gossett's so excited, right? Because he's going to get famous, he thinks. Okay, and so he's going to publish it, but then there's a problem arises, and the problem is Guinness beer, because it turns out that Guinness beer has a policy, because they had an earlier, not statistician, but an earlier scientist who had published his work, and then the competitors, the other breweries, had learned the work and had stolen it, basically. And so Guinness had started a policy that said, you can't publish any work that you made using, our brewery, unless there's no connection between the work and the brewery. So you can't have your name, it can't refer to beer or any part of our production. So because of that, Gossett is a little depressed because it means he's not going to get famous. But he agrees to let Sir Ronald Fisher publish this, but it has to be published anonymously to comply with Guinness's policies. And so he publishes it under the name Student. And to this day, the work, this test is often called the student's t-test or the student's t-distribution. And I'll tell you a funny story. When I learned this when I was in college, when I took the course you're taking now as a sophomore in college, and the professor started talking about the student's t-distribution, but he didn't tell this story that I'm telling you right now. And so I thought then, and I thought this until I started teaching statistics in high school, was that we were learning like a basic t-distribution, the student's t-distribution, but there would be another more professional t-distribution that once you got out of school, you can learn. I did believe that for a long time, but not true. Okay, so he publishes this as Student, and so we call this the student t-distribution. So I want to show you some pictures of the student t-distribution. So I'm going to do this on a calculator. So I hope this works. So here's what I want to do, okay? I'm going to go, and first of all, I'm just going to draw the normal curve for you. So, and I'm going to have to set the window here. So the window I'm going to set from, whoops, the window I'm going to set from -3 to 3. And then I'm going to do zoom fit, and that should just draw the normal curve like we're used to. So there's what we call the Z distribution, okay, the normal curve. That's what we're used to seeing, okay? Now I want to show you the T distribution, okay? So I'm going to go back up here. I'm going to go to this. I'm going to leave the normal up there because I want to compare this to the normal. And so I'm going to ask it now just to draw the T distribution. I'm going to, but now you need to tell it what I said is how many degrees of freedom. So let's say we're doing a sample size of 4, small sample, okay, whoops, small sample. And sample size of 4 means a degree of freedom of 3. And I'm going to make this, there we go. Okay, I'm going to make this dark so you can tell the difference between the two. So the lighter one is going to be the old normal curve, and now this is going to be the T distribution. So let me hit graph here, and let's see. So this is what Gossett hypothesized was happening here, okay? You'll notice it is normal-like. Okay, certainly very well behaved, symmetrical, just like the normal curve. But can you see here what I'm talking about, that it was fatter? Okay, in other words, if I took any particular place and said how much of the normal curve would I expect in that tail, the T distribution has slightly more area under it. So it's a little fatter in the tail. But if I change this now to a lot of degrees of freedom, so 50 degrees of freedom now, this would be a sample size of, I guess, 51. Let me show you what happens. If I could hit graph. There's our old friend, the normal curve. Here's the T distribution. And now you'll see like there's very little difference. Okay, that as the degrees of freedom gets bigger, this T distribution starts approaching the normal distribution. Okay, and this is all what Gossett was hypothesizing, not using math, using the experimental data that he's getting. Okay, so, okay, and now this is the result. Okay, this is what Gosset's result is. He says, okay, if you want to get a, if you want to do this by substituting an S instead of sigma, you can do this, but instead of it being a z-score now, it's going to be a t-score. Okay, but look, this formula is basically the same thing. Okay, it's the estimate minus the null hypothesis over now a standard error, an estimate of the standard deviation. Okay, the end of that story, by the way, with Gosset is he publishes it under student, and it's well received, and people start really realizing that maybe you can do this work with smaller sample sizes. But he never actually proved the math behind it. But it turns out Fisher, Sir Ronald Fisher, goes back 10 years later, I think, and actually is able to describe mathematically this curve. We don't do this in this class. It involves what's called gamma functions, okay? We don't do it in this class, okay? But the interesting part is when he does this, and he is able to describe mathematically this sampling distribution, the t-distribution, the shocking part is Gosset's numbers on the slips of paper that he was pulling out and the probabilities that he came up with were all correct, which to me is just a shocking end of that story. Okay, so anyway, there's a long story, but it's resulting now in the results that we are going to use. Okay, so here's our formula for a t-score. It looks shockingly like a z-score. Okay, and as the degree of freedom go to infinity, t becomes z. Okay, so this is the results of Gosset's work, and this is what we're going to use when we substitute S in for sigma. So let's go back to our problem now. You remember we were talking about cookies, right? So 10 grams of sugar is what the machine is supposed to do, okay? And they have taken 25 cookies. And now let's do our work. Now you'll remember now, I'm pulling this back up, okay? Because remember, this was our sample mean, and now here was our sample standard deviation, 3.959. This is not sigma, this is S. This is the standard deviation of the sample, okay, 3.959. Okay, but now we can just do this, can we not? So here's the t-score, okay? It's a t-score with 24 degrees of freedom. Probably should put that in, okay? It's a t-score with 24 degrees of freedom. And look, I've just calculated it, okay? So now I'm using a standard error, S over the square root of n, okay? And I got 2.38. Okay, well, that's kind of like a z-score, but now it's a t-score, okay? And so here's the question is, can I use the chart? And the answer is no, you can't use the chart because it's not a z-score, right? The chart was assuming the normal distribution. We're using a normal-like distribution, so we need another chart, okay? You can go find one of these charts, and I suggest you do. If you search, I don't know, t-distribution table, you'll come up with one. I have a link here to one. The easy way to get them, the way I get these is I just go to AP Stat free response and look at the back of any free response, and all these tables are here, okay? But let me show you a picture of one, okay? So here is a t-distribution table. Now we need a name for this, right? Because we can't call it the chart because it's not. So here's my name. It has a hand motion, so I need to make sure I'm on the screen. This thing is called the chart, just like that. You have to do the hand motion though, chart. So here we have a chart. Now, the chart is not as good as the chart. It can't be. Because if you wanted to make something as good as the chart, it would need to be a book. Wait, no hand motion. It would need to be a book. Why do I say that? Because there's a different t-distribution for every degree of freedom. And so we would need to have a different one of these tables for every single degree of freedom, okay? That's not what this is. And so let me show you what this is right here, okay? this has the degrees of freedom on the left, okay? Now you'll notice it starts jumping as you get up to higher sample sizes, because at this point you're going to see that you're going to start approaching the Z distribution, okay? This is most important when you have smaller sample sizes, okay? So we had a sample size of 25, and so we have a degree of freedom of 24, okay? Now, if you look up here, it has tail probabilities, and so what you have to do to use the chart is you have to go to your degree of freedom, and then you have to move over until you find about where your t-score was. So our t-score was 2.3 something. Okay, so we're right in between here. And so our p-value, our tail probability, is somewhere between 0.01 and 0.02. Okay, but remember, okay, this table has one tail probabilities. Okay, look at the picture. So that means I have to double my p-value. And so my p-value would be double that. And so I'm going to say the chart gives me a p-value of somewhere between 2 and 4%. Okay, that is a little unsatisfying for people, because it's more satisfying to come up with a p-value. And so if you want to actually get the p-value, what you need to do is go to technology. Okay, and so let me show you. Okay, so I'll start with some Minitab. Okay, so I'll go to Stat and Basic Statistics, and I'm doing now a one sample T. So I'm choosing one sample T. Okay, and you can do this in a couple ways. You can go to Summarize Data and just put in the sample size, mean, and standard deviation. But if you have the data in a sample, it'll do that in a column, it'll do that for you. So I'm going to go here and I'm going to choose sugar. Okay, and I'm going to ask it to do a hypothesis test for me. Okay, options, not equal to. Okay, and let's see. And we should get a p-value. Why did I not get that p-value? Oh, do you see it? Because I have the mean as the wrong. This is a mean of 15 and it should have been a mean of 10. In Minitab, if you hit Control E, it'll bring up the last thing. I have the wrong number here. Okay, the hypothesis should have been 10. So now let me try that again. Okay, oh, and there we go. So here is the actual p-value. And like we said, it was somewhere between 2 and 4%. In this case, it's 0.026. Okay. Let me show that to you on a calculator. Let me pull up my calculator here. So if I go to Stat and over to Tests, and now I'm going to find a t-test right there. And you have a couple choices here, just like in Minitab. You could, if you go to data, you can type the number in the list. I would put it in list 1 here. I don't really want to do that, but I could. If you go over to stats, you can just put in the numbers, okay? So the null hypothesis was 10. X bar was 11.84. The standard deviation was 3.959. The sample size was 25. And we have not equal to, and I'll hit draw. And let's see. I like this feature. I like a little bit better than Minitab because it draws it for you, which I think is nice. It shades. You'll notice it's shading a two-tailed shade and slightly different p-value. Again, never worry about small differences. Probably has to do with rounding. Okay, but between 2 and 4%, there we go. Okay, so if you want a p-value instead of a range of p-values, you probably shouldn't use the chart. If you want a actual p-value, you should use some sort of technology, okay? And I'm sure you can just search T calculator on the internets, and you can find many that will calculate a p-value for you, okay? Going back here now. So from the p-value is somewhere between 2 and 4%, but from technology, I'm going to get a nice p-value, which is 2.6%. Okay. Well, from now on, this is the same thing, right? I mean, so basically, we're doing the same thing we were doing before, but we can't use the chart anymore. After we substitute sigma for, S for sigma, we now have to use the chart. Okay. And so the p-value is 2.6%. Okay. I didn't write my decision in here. So what should I do? If the p-value is 2.6%, well, I think that that's pretty low. And so I'm going to reject the null hypothesis. Okay. And I'm going to pull this back. Okay. And so you write it. Okay. So write the conclusion and see if you can do it. Pause the video and see if you can write this conclusion. Here's what I got. If I assume the machine is working as designed and mixing in 10 grams of sugar, maybe I should have said 10 grams of sugar per cookie, okay? There is only a 2% chance of seeing results like seen here. That's so low, so this study suggests that the machine is not working as designed. There you go. Again, notice in my conclusions, no statistics words, okay? Just explaining the conditional probability and then saying what my results are. Okay, so there you go. But we never talked about the assumptions. And there's one part of the assumptions here that's a little bit tricky. And so I want to go through that carefully with you. Okay, so let's look at the assumptions for a one sample t-test. Okay, the first one is the same. Okay, if we're sampling without bias, to assume that mu x bar equals mu, same as before. Okay, this is also same. Independent picks, including the 10% condition. By the way, you notice I'm not talking like we did in the last chapter about experimental groups, because this is a one sample test, right? So you're not doing any comparing of one sample to another. Okay, when we get to the next lesson, when we get to doing comparing two means, now we're gonna have to consider whether or not we're sampling or whether or not we're using experimental groups. Okay, in this case, it's gonna be sampling. So independent picks, including the 10% condition, so we can use that. So those two assumptions are the same. The third assumption is a little bit different because of the t-test, so I wanna just go through this with you, okay? I often find my students never quite get this. So I'd really like you to pay close attention to this next part, okay? So, okay? The assumption itself is that we can use the t as long as the population is normal. But that's not too helpful because you're not going to know that the population is normal, right? It's very unlikely that you know the shape of the population. But it turns out that the t-test is robust. I'm not sure if I mentioned that word before, the statistics word robust. Robust means you can violate an assumption, and as long as you don't violate it too much, the procedure still works. That's what robust means. For instance, there's no test that's robust to that first assumption. Like if you have bad data, if you have biased sampling, there's no way to fix that, okay? But it turns out for this third assumption that the t-test is quite robust, that it doesn't necessarily need a population that's extremely close to normal distribution, okay? And so this involves the central limit theorem, what we learned before, but here is the guidelines, okay? And here is how we do this, okay? And so this would be assuming you don't know the shape of the population. If you do know the shape of the population and you know it's a normal population, you can go ahead and use the t-test, okay? But in most cases, you're not gonna know the shape of the population, okay? So here's what we're gonna say. If the sample set is large, and this is your textbook's numbers, there's, again, nothing magic behind these, okay? But he says if n is bigger than 40, okay, then the central limit theorem says that we can just use the t distribution for the sampling distribution. Okay, so if I had a large sample size, I would say something like, I don't know the shape of the population, but with such a large sample size, I can approximate the sampling distribution with t. Okay, but it gets better, okay, because we can still do this if the sample size is medium. So if we have a medium sample size, which would, in the cookie case, this is what we have, right? Because we have a sample size of about 25, okay? the central limit theorem allows us to use the t as long as we don't have any evidence that the population is very, very naughty. That would mean highly skewed, weird gaps, many, many outliers, things like that. Now, how would we get that evidence? Well, maybe we know something about the situation we're doing, or maybe we're just going to look at the sample and see what that shows. I'm going to talk about that in a second. But if we have a medium sample size and we don't think the population is very, very naughty, then we say we go ahead and use the t. Okay, if you have a small sample size, and by the way, these are the sample sizes that Gossett was working with. If you have a small sample size, less than 15, then in order to go ahead and use the t, you probably need to have some evidence that the population is well behaved. Sometimes you'll see, like in textbooks with very small data sets, they'll draw a histogram of the sample. I get very hesitant with that with very small sample sizes. I would like to have some other knowledge about what roughly the shape of the population is, okay? But you're supposed to have some evidence, not that it's not too naughty, but that it is really well behaved. Okay, so this is the third assumption in a t-test. And I'm going to show you now how I'm going to explain this. And I'd really like you to follow this template, okay? So here are how I'm going to write the assumptions for this problem, okay? First is random. The problem didn't tell me how the cookies were chosen. I just don't know how they did that. I would need to know that they were chosen randomly so I could assume that mu x bar equals mu. Okay, the 10% condition is met, but I just don't know. Like, were they all taken right off the assembly line at the same time? I just don't know any other issue about the other issues of independence. So I would need to know those to know that mu x bar equals this. And now the third one. So please look at how I write this and try to duplicate something along this lines, okay? I don't know the shape of the population. That's the first thing, okay? Then the sample size comes in, but n equals 25 is medium and not large. So then I need to look at some picture of the sample. This is the third rule of statistics, right? Which is make a picture. Okay, so I'm adding in a picture right here. And now I'm telling you what I think about this picture is it looks pretty well behaved to me, up and down. So that's suggesting that maybe the population is not extremely naughty, and so I can go ahead and use the t-distribution. So I would like you to have your third assumption look something like this, with a picture, okay? You can use a box plot here as a picture as well. I like the histograms better to talk about shape than I do a box plot, but you need some picture of it. So try to make your assumptions look like this, okay? All right, well, we're almost done. Let's see. Oh, we didn't make a confidence interval. So remember, let's make a 95% confidence interval for the true amount of sugar. Let's see, there are 3 steps, right? Assumptions, showing your work and conclusion, but we've already done the assumption, so I really only have 2 things. I got to show my work, and then I got to conclude. And again, you should be able to do this right now. You should be able to stop this video and do this right now if you understand what a confidence interval is. Okay, so here we go. Okay, there's the formula for every confidence interval. The estimate plus or minus the critical value times the standard error. What's our estimate? Well, here it is in formula. So x bar, that's our estimate. Critical value, t star, in our case, t star 24. Standard error, but I don't know sigma, do I? Okay, so what am I going to have to do? I'm going to have to use S. Okay, so 3.884. I guess I should have written S here. Right, because this is the standard deviation, right? When we have the standard error, we have S right there, okay? Putting in my numbers now, 11.884 plus the critical value, 3.959. That's the standard deviation over the square root of n. But what's the critical value? Okay, so you know if we were doing a z-test, it would be 1.96. But remember, the tail in a t is a little bit fatter. So we're going to get a little wider interval in order to get 95%. So we need some number that's a little bit bigger than 1.96. And where do we get that number? This is where the chart is really helpful, okay? Because these are t stars. These are critical values, okay? And so I want 95% confidence. So if there's 95% confidence, that's 2.5% in each tail. So if I go to tail probability of 2.5% and a degree of freedom of 24, there it is. And you'll notice it's a little bigger than 1.96. In this case, 2.064. So, but a couple comments. First of all, this particular t-distribution table is idiot-proof, because you'll notice I had to figure out that each tail was 20.025. But they help me actually, because on the bottom it tells me that that corresponds to a 95% confidence level. But the other thing I want you to notice is, as you go up on this table, these numbers are getting bigger. That's important, right? Because fewer degrees of freedom, it's departing from normality more, okay? And the tails are getting a little bit fatter, and the standard the confidence interval is going to start to get a little bit wider. Okay, you can think about that as, yeah, that makes sense, because I made another like fudge. I've substituted S in for sigma, which is yet another fudge. And so I should be getting slightly wider confidence intervals to account for that. And that's what you are. The other thing I want you to notice is if you go to the bottom, and I'm not sure if you can read that here, but that says infinity. If you have an infinite number of degrees of freedom, that's the Z distribution. And so the numbers you see down here, these are the Z stars, right? Here it is, that's the 1.96. Here's the 1.645, right? These were numbers that we were using when we're using Z distributions. And so what that is as the degree of freedom goes to infinity, now you have your Z distribution. And so you'll notice if you have a very small sample size, a sample size of like in the hundreds, you'll see that like there's very small difference between using the T and the Z. Okay, but the smaller the sample size, the more difference there is. So I got it. So here's my T star, which is 2.064. Whoops. Okay. Sorry. 2.064. And that gives me a confidence interval of 10.25 to 11.52. And now all I have to do is conclude. So stop the video and see if you can write a conclusion. Here is my conclusion. I'm 95% confident that the machine adds in between 10.25 and 13.52 grams of sugar. This means if I took many samples and made an interval of each time, 95% of those intervals would contain the true mean. And now let me show you this on technology. So back to Minitab. Pull this up again. I don't want to perform a hypothesis test anymore. But I do want to check that it's, oh, look, this is 90% confident. So I'm going to change it to 95% confident. And there's the numbers we got. Okay, there they are. And again, you know, feel free to use these things, but you're still in statistics class, so I still need to see work from you. I need to know that you understand where these numbers are coming from. And after you leave this class, then you can just use technology from the get-go. But right now, I want you to show your work. Feel free to use these to test yourself. Okay, let me pull up the calculator. And let's see, I'll go to stat, I'll go to tests, and I gotta find a T1 proportion, T interval, there it is. Hit enter. Okay, let's see, go over to stats. I had to reset this. If you haven't reset your calculator, probably these numbers are already there. But 11.84, it needs to know the standard deviation. By the way, you'll notice it's not asking you for sigma, right? Because you're doing a t-test. So it knows that you need to be using S. Okay, N was 25, confidence level was 95%. And that should give me something around what we got. Okay, small differences, don't worry about it. Okay, so there's technology to try to get these. Okay, and that's it. Okay, so that's how you do a t-test. I hope that you are really understanding that we're not really doing anything new. Okay, slight difference. We've gone from Z to T, but basically we're doing the exact same thing. Okay, So to sum up here, and then I'm going to have you do one sample problem, okay? When do we use T and when do we use Z? Okay, so you use T when you don't know sigma and you're substituting in S. That's been the point of this discussion. But in reality, it's very unlikely that you know sigma, right? Because we're doing this test on what the mean is. It would be a very odd situation that you have to hypothesize what the mean is, but you know what the standard deviation is. I mean, I suppose that might be possible, and then you don't need a T. But in most cases, we're not going to know that. Okay, at least let me be clear. Most cases about means, we're not going to know that. So here is the pretty good rule of thumb. If you have means, use T. We still use Z for proportions because you remember in proportions, we don't have this whole problem because the standard deviation is dependent on what the parameter is, right? It's square root of P cubed over N. So whatever the P is, that tells you what the standard deviation is. The means are different because the standard deviation is independent of what the mean are. So here is our pretty much always used rule of thumb. Use T for means and use Z for proportions. There is a special case of using Z for means if you know what sigma is. But on a practical case, we don't do that. Okay, so T for means and Z for proportions. That's what I want you to get from here. All right, time for a sample problem. So this is about shoes. They know that their shoes are last 15 months. That's a long time for a shoe to last. Well, I guess not. A sneaker doesn't last that long, but other shoes might. Okay, so they're going to make a new shoe that's supposed to last longer. Pay attention, right? That's going to be about your alternative hypothesis. They take a random selection of 30 sneakers. Again, that's a medium-sized sample. Okay. The data's in the handout folder. It's called shoes. It's like before, it's an Excel file, so you need to get it into some sort of statistics program. I mean, another thing, if you want to use your calculator, look at the Excel file and type in the numbers into your into a list on the calculator, and that'll work too. That's just 30 numbers you need to type in. Okay, and so we want to know is his claim of a better shoe supported? We want to do a two-tailed test. No, that's not right because it wants to be better. Okay, so we want to do I'm going to take that out, that two-tail part, because he said, is it going to be better? Okay, so you're going to be doing, I think, a one-tailed test with a significance level of 5%, and then I want you to calculate a 90% confidence interval for the true lifetime of the new shoe. Okay, so you need to get the data, shoes, and then I want you to do the 5 steps of a hypothesis test and then a confidence interval. Stop the video and then come back when you're done and I'll go through the answers I got. All right, here we go. Here was the data I got. I got a mean of 16.094, which is a little bit bigger than 15. We'll have to see if it's bigger enough. Standard deviation of 2.41. Now looking at this histogram, this one makes me feel a little bit unsure about this because, and I'm going to talk about this in the assumptions, but this looks like a little bit skewed to me. I see that skew in the box plot. Okay, so let's get started. Okay, here are my hypotheses. They claimed it was 15, and I want to know, is it bigger than 15? Here are my assumptions. I said shows. They chose the shoes randomly. And so I'll assume that mu x bar equals mu. The 10% condition is met. God, I have so many typos here. I don't see any other reason independence would be violated. So I'll go ahead and assume that the standard deviation formula is right. Now, again, I don't have a problem with the way I'm writing it here, right? This isn't the formula I'm going to use. I'm going to use S over root n. If I had that, I should use some sort of approximate sign here. But now I'm just stating that this formula is correct. Okay, so as long as I have an equals here, I can use sigma. And now that third assumption, did you write it right? Let me show you how I wrote it. Okay, I don't know the shape of the population. N equals 30 is medium. And I said I saw some significant skewness in the data set. So maybe there is in the population. So what that seems to me is like the sample size isn't big enough for the central limit theorem to take care of the skewness and to approximate the sampling distribution with a t. Here's my work. X bar minus the hypothesized mean of 15, a t-score of standard deviation of 2.415 over root 30. I got 2.48, 29 degrees of freedom because n was 30. I got a p-value of 0.01. I didn't need to double that because I'm doing a one-tailed test, but anyway, it's quite a bit less than my significance level. So I'm going to reject the null hypothesis. Here's my conclusion. If I assume the new shoe doesn't last any longer than the old shoe, that's the null. There's only about a 1% chance of getting these results. Since this is pretty low, I do have evidence to suggest the new shoes last longer. But since that assumption was violated, I think the study should be done with more sneakers. There's my conclusion. 90% confidence interval. So I did it again here. This should be S. This should be S. Here's my formula. Okay, S over root n. I got a t star of 1.699 when I looked on the chart. Okay, and that got me 15.344 to 16.842. And then here's my conclusion. I am 90% confident that the new shoes last between 15.344 and 16.842 months. This means if I took many samples and created intervals, 90% of those intervals would capture the true average lifetime. How did you do? Did you do everything right? Hopefully you did. I wanted to show you something about this on Minitab that I noticed. The new edition of Minitab does something a little bit differently than our old ones did, and I wanted to show you this, okay? So here is the shoes, okay? When you do a one sample T, and now I'm asking it to put it in the column, I'm going to pick shoes. I'm going to ask it to perform a hypothesis test with a mean of 15. And I'm going to do an option. We said 90% confidence interval. And the mean is bigger than the hypothesized mean. Now I get the p-value that I got, which was 0.01. A t-value that I got, which was 2.48. That was all good. But this number is different than what I got. Okay, and the reason is I just figured this out, that Minitab 19 does this. If you do a one sample test and you ask for a 90% confidence interval, it puts the whole 90% on one tail. Okay, in essence, it's doing a one-tailed confidence interval, which is not generally what we want. Okay, so if you want the actual confidence interval with 5% on each side, you have to either unclick the hypothesis test, or you can change it to not equals to, okay? But if I unclick this hypothesis test, okay, it will not work. Hold on a second. If I unclick this hypothesis test, okay, and click OK, no, that doesn't work, okay? So what you need to do then is go to options, change it to not equal to, and let's see if that works. Okay, and now you're going to see here is the actual hypothesis test. I'm not sure if there's an option somewhere in Minitab to switch this. I haven't found it. That's what I noticed with fooling around, because these are the numbers that we got. 15.344 and 16.852. Anyway, I just noticed that in the new version of Minitab. All right, so that's all I got. Okay, so that's chapter 23. Hopefully you find this stuff pretty easy if you understand what we've been doing up until now. But you should do chapter 23, which is on one sample t-test. So with that, I will say peace out.